We've now arrived at a slightly more formal part of our journey. From here on, we'll be spending more time with definitions and structure, really starting to see how group theory fits together as a mathematical system. But don't worry, everything we're doing builds directly on what you've already seen. Let's start by recalling where we are. In modular arithmetic, we saw that in the group Z5, integers mod 5 under addition, we could start with the number 1, and by adding it repeatedly, generate the entire group. So 1 to 2 to 3 to 4 to 0. That's the idea of a generator. A generator is an element of a group that, when the group operation is applied repeatedly, produces every element in the group. So here's our next formal idea. A cyclic group. A group is cyclic if it contains at least one element, a generator, that can produce the entire group through repeated application of the group operation. In Z5, 1 is a generator, but so is 2. For instance, we can add 2 to 2, we get 4. We add 2 to 4, we get 1. Add 2 to 1, we get 3. Add 2 to 3, we get 0. And we get our entire set, it's just in a slightly different order. This is what we mean by a cyclic group. You can think of it as a loop that can be spun all the way through using a single motion. But not all groups work this way. Some groups are non-cyclic. That means no matter which element you start with, repeating it won't produce the whole group. A great example comes from real life, the Rubik's Cube. The Rubik's Cube group includes all possible states the cube can be in, and all the legal moves that can transform it. But if you just repeat a single move, say turning the right face over and over again, you'll eventually return to your starting state. But you'll never visit every possible cube configuration. That's because the Rubik's Cube group is non-cyclic. No one move gets you all the way around. You need combinations of different moves to fully explore the structure. Also, and this is important, in the Rubik's Cube, order matters. Doing one move and then another isn't the same as doing them in the reverse order. We'll come back to this when we talk about a group being abelian, but keep that in mind. Now, earlier we used modular arithmetic as a clean, memorable example of a cyclic group. So, what's the standard example of a non-cyclic group? Well, there really isn't one. Non-cyclic groups are too varied and complex to have a single go-to example. The closest we can come is a permutation group, which captures all the different ways of rearranging elements. We'll define permutation group precisely in their own section, but for now, think of them as a mathematical backbone behind things like card shuffling, Rubik's Cubes, and password scrambling. So here's what to take with you from this part of the video. Cyclic groups can be generated by a single element. Non-cyclic groups can't. Modular arithmetic gives us a great mental model for cyclic groups. More complex systems like the Rubik's Cube or permutation groups are non-cyclic and demand more structure. And that brings us to another important idea, whether or not a group's operation depends on order. In the next section, we'll define exactly what it means for a group to be abelian, explore how that shapes the way a group behaves. In the last section, we explored the difference between cyclic and non-cyclic groups, whether a group can be generated by a single element, or whether its structure is too complex for that. Now, we're going to examine a different but closely related question. Does the order in which we apply the group operation matter when combining elements? That is, if we combine two elements one way, do we always get the same result if we reverse them? This gives us another way to classify groups. And just like with cyclicality, this distinction reveals something meaningful about a group's internal structure. Let's define it. Abelian group. A group is abelian if for all elements A and B in the group, A times B equals B times A, where the dot in the middle is the group operation. This property is called commutativity. The idea that swapping the two elements doesn't change the result of the group operation. We've already seen several abelian groups. The integers under addition, Z5 under addition modulo 5. In fact, any Zn under addition mod n will be abelian. But these are all cyclic as well. So now, Let's now look at a group that's abelian but not cyclic, one that's extremely familiar. The real numbers under addition. We'll call this set R. This group is clearly abelian. A plus B equals B plus A for any real numbers A and B. And we have 0 in there, so there is an identity. We have inverses. All the things that make it a group. And it's abelian. But is it cyclic? Suppose it is. That would mean there exists some real number R such that by adding R or subtracting it repeatedly, we could reach every real number. Try R equals 1, we get all the integers, but not fractions or decimals. Try R equals 1/2, now we get half integers like 1/2, 1, 1.5, but still no 1/3, no √2, no pi. And as we decrease our step size, it helps us get more resolution, but even then we're only hitting numbers that are built from that base. There are always more real numbers just out of reach. No matter what value of R we choose, we'll always miss something. There's always a real number between the ones we can generate. So R under addition is abelian, but not cyclic. There's no single element that generates all of it. Let's now go in the other direction. What happens when a group isn't abelian? We define abelian groups as those where combining A and B gives the same result as combining B and A. So to be non-abelian, we just need one counterexample. Pair of elements where A times B does not equal B times A. Let's revisit the Rubik's Cube. Suppose we perform move R, turning the right face, and then move U, turning the top face. Now reverse that. U first, then R. Even though we're using the same two moves, the final state of the cube is completely different, depending on the order in which we apply them. That's what it means for a group to be non-abelian. It's not about violating some algebraic nicety, it's about the behavior of the group depending on the sequencing of actions. So the Rubik's Cube group is non-abelian because the order in which you apply operations genuinely affects the outcome. Now that we've seen abelian groups, non-abelian groups, cyclic groups, and non-cyclic groups, it's natural to ask, how do these properties relate? Well, not all abelian groups are cyclic. We just saw that with the real numbers. But here's something that is true, and it's worth proving. Every cyclic group is abelian. This will be the first formal proof in the series. Let's take it slowly. Suppose G is a cyclic group generated by an element G. That means every element in the group can be written as a power of G. A equals G to the M, B equals G to the N for some integers M and N. Now compute their product. A times B equals G to the M times G to the N equals G to the M plus N, and B times A equals G to the N times G to the M equals G to the N plus M. And addition is commutative, so M plus N equals N plus M. And so we have G to the M plus N equals G to the N plus M, so A times B equals B times A. So all elements commute, and the group is abelian. This is a key insight. It tells us that cyclic structure guarantees commutativity. If a group is cyclic, it must be abelian. This also explains something from earlier in the video, why we have such a clean universal example of cyclic groups, modular arithmetic. Because cyclic groups are built from a single element, they behave in predictable, repeatable ways. It's easy to model them, easy to visualize, easy to work with them. But once you leave that world into non-cyclic groups, the structure becomes more intricate. That's why we don't have one go-to example of non-cyclic groups. They vary widely. Their behavior isn't governed by one element, but by combinations, overlaps, constraints. To start making sense of that, we need a richer family of examples, especially ones that help us think in terms of sequences and rearrangements. In the next section, we'll look at the permutation group, the set of all ways to rearrange a collection of objects. Permutation groups are among the most fundamental non-Abelian groups in mathematics, and while they're not cyclic, they're rich with substructure, including subgroups that are cyclic, or even abelian. So next we'll explore the group of permutations, how it works, how it breaks commutativity, and how it helps us navigate the complex world of non-cyclic, non-Abelian groups. Up to this point, we've mostly looked at groups where elements were familiar. Numbers, geometric transformations, or puzzle movements. Now we're going to change perspectives a little bit. In the permutation group, the elements of the group aren't objects being manipulated. They're rules, precisely defined instructions for how to rearrange a set. Imagine a deck of cards, numbered 1 through n. Permutation isn't a new set of cards. It's a plan for rearranging the old ones. Put the second card in the third spot, move the first card to the bottom, and so on. Each of these rearrangements is an action, and we can treat those actions as elements in a set. Then we define a group structure based on how these actions combine. So what is a permutation group? The group of all permutations of n elements under composition is called the symmetric group. We denote it Sn. Let's break that down. We begin with a fixed set of n elements, like 1, 2, 3, so on to n. A permutation is just a rearrangement of that set. If you list all possible rearrangements, you'll get exactly n factorial different ones. What makes this a group is how we combine permutations. The group operation is composition. The same kind of composition we were dealing with the sliding tile puzzle. You perform one permutation and then immediately follow it with another. This composition is associative. There's an identity permutation that does nothing. Every element stays in place. Every permutation has an inverse that undoes it, and composing any two permutations gives another valid permutation. So all permutations of n elements with composition as the operation form a group. This group is called the symmetric group, and we write it as Sn. But writing these permutations as full before and after tables is unwieldy, so mathematicians use a shorthand called cycle notation. Cycle notation. 1, 2, 3 means 1 goes to 2, 2 goes to 3, and 3 goes to 1. For example, 1, 2 means swap 1 and 2. Everything else stays fixed. The identity permutation, where nothing moves, can be written 1, 2, 3, or just left unwritten. If a number isn't mentioned in the cycle, it's understood to stay put. Cycle notation is concise and exposes how each piece of the permutation behaves. It's especially useful when composing permutations, which brings us to an important question. When we compose permutations, in what order do we apply them? Left to right? Right to left? The answer is both approaches are valid, depending on your conventions. Some authors prefer to read permutations left to right. First apply the cycle on the left, then the one on the right. Others, including me, prefer to apply them right to left. That is, if you see 1, 2, 2, 3, you do 2, 3 first, then 1, 2. This matches the behavior of function composition in most mathematics, f of g of x, where g is applied first. So, throughout the series, we'll use right to left composition. Let's see an example. Take the permutation 1, 2, 2, 3, and apply it to the element 1. We apply 2, 3 first. 1 isn't in 2, 3, so it stays 1. Then we apply 1, 2. Now 1 maps to 2. So the result of 1, 2, 2, 3 acting on 1 is 2. Now reverse the order. Apply 2, 3, then 1, 2. You don't get the same result. So the conclusion is that S3 is non-abelian. This is the first group we've studied explicitly where combining elements in different orders produces different outcomes. We saw similar behavior in the Rubik's Cube group, but here in S3 it's fully visible and easy to compute. That makes permutation groups a powerful and approachable starting point for understanding non-abelian behavior. So why study them? Because there are most accessible examples of groups where the elements are actions, not objects. The operation composition is meaningful and intuitive. Non-abelian structure arises naturally and can be tracked explicitly. They're small enough to compute by hand, but rich enough to reveal deeper patterns. In short, permutation groups gives us the clearest window into what happens when a group's behavior becomes more dynamic. And there's something else. Although Sn is non-abelian and non-cyclic for n greater than or equal to 3, it contains subgroups that are cyclic or abelian, or both. That leads us to our next topic. In the next section, we'll explore the idea of a subgroup. A smaller group nested inside a larger one. We'll see how subgroups give structure to the whole, and how studying these internal pieces can help us understand the complexity of the full group from the inside out. In the last section, we explored the permutation group Sn, our first group built from transformations rather than static objects. We saw that even though the full group is non-abelian and non-cyclic, it still contains smaller pieces that behave like groups on their own. Today we're going to focus on those smaller pieces. We're going to talk about subgroups, groups within groups. Let's define it carefully. Subgroup. A subset H of a group G is a subgroup if it forms a group under the operation inherited from G. That means H contains the identity element of G. It's closed under the group operation. If A and B are in H, then so is A times B. Every element in H has its inverse in H. In short, a subgroup follows all the same rules as a group, using the same operation, but it lives entirely inside a larger group. The larger group is sometimes called the supergroup, simply to distinguish it as the group that contains the subgroup. Let's look at some examples. Start with the integers under addition. This group has many subgroups. One of the simplest is a set of even numbers, which we can write as 2z. It includes 0, the identity. It's closed. You add any two even numbers, you get an even number. And it includes inverses. -2 is the inverse of 2. So 2z is a subgroup of z. Now look at z6, which is the integers under addition modulus 6. This group has several subgroups. For example, 0. The group with just the identity element is a subgroup. We also have 0, 3. Because 0 plus 3 is 3, and then 3 plus 3 is 0. 0, 2, 4, and the full group. Each of these is closed, contains the identity, and includes the necessary inverses. We'll explore visual ways about this kind of structure in the next episode. But not every subset of a group is a subgroup. Let's look at a non-example, the set of odd integers, written 2z plus 1. This is the set ... -3, -1, 1, 3, 5, so on. At first glance, it looks structured, it's infinite, it's regular, but it's not a subgroup of z. Why? It doesn't contain the identity element, for one. There is no 0 in the set 2z plus 1. And it's not closed under addition. 1 plus 3 equals to 4, which isn't odd, so it isn't in the set. So it fails the basic requirements. It's a structured set, but it's not a group under addition, and therefore not a subgroup of Z. This shows a key idea. Regularity doesn't guarantee group structure. A subgroup has to be stable under the operation, no exceptions. Let's return to permutation groups for a moment, specifically S3. This group has several interesting subgroups. One example is the identity permutation and 1, 2. This is a set with just 2 permutations, the identity and the transposition that swaps 1 and 2. If you apply 1, 2 twice, you get back to the identity. The structure closes in on itself. This is a valid subgroup. And I also would like to point out that it is a cyclic and abelian subgroup. Another subgroup is the identity permutation 1, 2, 3, and 1, 3, 2. This one is cyclic. You can get all three elements by repeatedly applying 1, 2, 3. So, any element of a group generates a cyclic subgroup. So even in large complex groups, every single element generates a small self-contained subgroup. Also notice this subgroup is abelian, even though S3 as a whole is not. That's another important point. A subgroup can have different structural properties than the larger group it lives in. So why do they matter? Why do we look at things like that? Because they give us a way to break complex groups into manageable pieces. Big groups can be difficult to study directly, but smaller groups, especially cyclic or abelian subgroups, can be analyzed on their own terms. Then we piece together what we've learned to understand this larger system. Subgroups also gives us a framework for classification. Many ideas in group theory boil down to understanding how a group is built from its parts. So far, we've talked through group behavior with examples, and we've relied mostly on intuition, diagrams, and straightforward arithmetic. But from here forward, we'll need a stronger toolkit, a more precise language to describe group structure. In the next episode, we'll focus on building that language. We'll introduce algebraic notation, learn how to express ideas clearly, and start using diagrams that help visualize how groups and their subgroups interact. We've seen groups behave, now it's time to learn how to speak their language. Let's wrap up. Let's take a moment to step back and look how far we've come. We began this episode by defining what a group is. Just 4 simple properties: closure, associativity, identity, and inverses. From there, we explored how those properties show up in everyday systems: clocks, puzzles, numbers, and symmetries. We looked at the history of group theory, how ideas about symmetry and solvability shape the way we think about mathematical structure. We dug into modular arithmetic as our standard example of a group, and from there we built our understanding of cyclic versus non-cyclic groups, whether a group can be built from a single repeating element or not, abelian versus non-abelian groups, whether the order in which we combine elements affects the outcome, permutation groups as a model for structured rearrangements, and most recently, subgroups, smaller groups living within larger ones, carrying their own patterns and relationships. At this point, you've seen a lot of what group theory has to offer at the conceptual level. You've built intuition, you've seen examples, you've watched structure emerge from just a few simple rules. In the next episode, we're going to shift gears a bit, from ideas to language. We'll introduce the notation and visual tools that mathematicians use to express group ideas clearly and precisely. You'll learn how to write down the structure of a group, how to describe a subgroup algebraically, how to diagram group behavior, and how to begin thinking about even more complex structures using the same basic vocabulary we've been building all along. We've built our intuition, now it's time to give that intuition structure. Let's get ready to speak the language of groups. Meanwhile, here are some exercises for you to try. Let r\0 represent the set of real numbers excluding the number 0. Do the real numbers under addition form a group? Do the real numbers minus 0 under addition form a group? Do the real numbers under multiplication form a group? Do the real numbers minus 0 under multiplication form a group? If you got ideas, answers, or questions, drop them in the comments. I'd love to hear how you're thinking through these, and it's a great way to join the conversation as we build this series together. And don't forget to hit that subscribe button. See you next time.